Hi, welcome to Gravitational Fields Lesson 7a. Today we're going to be finishing the last part of gravitational fields, and in the second lesson I'm going to show you how to do the question that I'm going to ask you at the end of this lesson, and then I'm going to give you your revision homework for the topic as a whole, and next time you see me we're going to be doing electric fields. How exciting! So today's lesson is all about escape velocity. Escape velocity is the speed at which you need to be going to get out of the gravitational field of normally a planet. So you are stuck on Earth. You jump and you come back down again. That's just really tedious. If you jump really fast, you'll still probably come back down. But if you jump really fast and you've got like a massive amount of momentum and speed right at the start, you'll keep going and going until eventually you're outside of the gravitational field of the planet. So, escape velocity assumes that you begin with all of your speed. Now this doesn't actually happen in an actual rocket, because if you think about a rocket, it's continually putting energy in all the way up. Engines just sort of crushing. Escape velocity assumes it's more like you were on a sort of spring. Imagine there's like a sort of board with springs under it, and you went bonk, and you were given all your energy right at the beginning, so that you were given that speed right at the start. It also assumes that you get all the way to infinity. You get completely out of the gravitational field. Whereas in practice, you don't need to do that. If you're flying to the moon, you only need to be going fast enough to get into the gravitational field of the moon, and then the moon will start pulling you. You don't need to get all the way out of the gravitational field of the Earth. The moon, of course, we know is inside the gravitational field of the Earth because it rotates around the Earth, so it must be. So, escape velocity is defined as the speed you have to have at normally the surface of the planet, but you can start at any point you want. So we could do escape velocity from the top of Everest, which will be a tiny bit slower, because you'd already done some work getting out of the field. It assumes that you have all of your speed at the start, and it assumes you get all the way to infinity. So that's how it's defined. Let's look at some maths. So what we're saying is at the beginning, you've got some amount of kinetic energy. So that's going to be equal to half mass times velocity squared. We also know that in the field at that point there's going to be a potential of minus gm over r. If we want to know how much potential energy a piece of mass has, remember the potential is defined as joules per kilogram, so we times that by the mass, and that will give us the amount of potential energy that it has. This is G big M little m over R. That's the potential energy that you have at the surface, half mv squared. That's the energy you've got. If this is greater than this or equal to, then you're sorted. So we can just flip that around the other side, put them equal to each other. The m's are going to cancel, which means if you think about it, escape velocity is independent of your mass. If you had one of those spring sort of jack-in-the-box things, and it sprung up with enough speed to get out, both light things and heavy things would get out of the gravitational field. So it doesn't matter the mass cancels, take the 2 over, v squared is 2gm over r, so our escape velocity in general is going to be root 2gm over r, where m is the mass of the planet, r is how far away you started, g is just the gravitational constant, and v is your escape velocity. So that's how we get to that. Right, we've got the kind of classic escape velocity question underneath. Have a go at that. I'll see you in the next lesson.